Tonight, we're going to explore one of the strangest facts ever uncovered about the place you live. A fact so quiet and so enormous that most people go their entire lives without ever hearing it. You are moving right now. Not just spinning with the Earth, not just orbiting the Sun, not just drifting with the Sun around the center of our galaxy. All of that is happening, yes. But underneath all of it, there is a deeper motion, a vast and silent fall, and it is carrying you and the Earth and the Sun and the entire Milky Way galaxy, every one of its 400 billion stars, in one direction through the universe at more than 1 million miles per hour. We are being pulled. Something out there across an unimaginable gulf of space is drawing our entire galaxy toward it, and has been for the whole history of the Earth, and will go on doing it long after. And here is the part that has unsettled astronomers for 40 years. We cannot see what it is. It sits in the one direction we are least able to look, hidden behind the bright body of our own galaxy. And for decades it had no name except the one a small group of astronomers gave it, almost in awe when they first realized it was there. They called it the Great Attractor. Tonight we're going to fall toward it together, slowly, the way the galaxy itself is falling, and we are going to find out what it is. By the end of tonight, you are going to understand exactly how fast we are moving and how we measured a speed that nobody can feel. You are going to understand what the Great Attractor turned out to be and why we still cannot see it directly. You're going to understand that our galaxy belongs to something far larger than most people ever imagine, a vast structure with a name that means immense heaven, and that even the Great Attractor is not the end of the story, because there is something bigger pulling beyond it, and something stranger still, a great emptiness that may be pushing us from behind, and you are going to understand by the time we are done why none of it will save us, and why that turns out to be a strangely peaceful thing to know. This is a journey through the largest motion you are part of and never noticed. There is no need to follow every number. There is no test at the end. The only thing tonight asks of you is that you let your body grow still while your sense of where you are grows very, very large. Before we begin, if you find these slow journeys through the real universe help quiet your mind at the end of the day, take a moment to subscribe so the next one can find you when you need it. If you are listening on Spotify, the follow button does the same quiet work, and it helps more people discover these long drifts through the dark than you would think. That is all. Settle in, lower the lights, let your breathing slow. Now, let's begin where every honest version of this story has to begin, not with the thing pulling us, but with the discovery that we were moving at all, because for most of human history, we had no idea. We thought, reasonably, that we were still. For thousands of years, the Earth felt like the fixed center of everything, and the heavens turned around it. Then we learned the Earth turns, and we learned it orbits the Sun. And we learned the Sun is one star among hundreds of billions, sweeping in a great, slow circle around the heart of the Milky Way, a single orbit, taking more than 200 million years. Each of these discoveries took something we thought was still and revealed it to be in motion. And each time it was natural to assume that surely now we had found the thing that did not move. Surely the galaxy itself, that vast wheel of stars, was at rest in the universe. By the end of tonight, you are going to understand how recently all of this became known, because the story of our great fall is, in the long view, astonishingly young. For nearly the whole of human history, no one had any idea that we were moving through the universe at all, let alone toward a hidden mass in the south. Go back just 100 years to the early 1920s, and astronomers were still arguing about whether other galaxies even existed. The faint spiral smudges in the sky, the ones we now know are island universes of billions of stars, were thought by many to be small clouds of gas within our own Milky Way. There was a famous debate about it, and it was only settled when Edwin Hubble, using the Great Telescope on Mount Wilson, proved that the Andromeda smudge was far too distant to be inside our galaxy, that it was a separate galaxy entirely, unthinkably far away. In a single stroke, the universe grew from one galaxy to countless galaxies, and the modern picture of the cosmos began. Then, through the rest of the 1920s, Hubble and others discovered that those galaxies are nearly all rushing away from us, and the farther ones faster, the expansion of the universe, the Hubble flow. So, within a single remarkable decade, humanity learned both that other galaxies exist and that the whole universe is expanding. But even then, even knowing the galaxies fly apart, no one yet suspected the hidden currents underneath, the local streaming, the Great Fall. That took another half-century. It was not until the 1970s and 1980s, with the work on galaxy distances and the discovery of the cosmic background dipole, that astronomers realized our galaxy has its own private motion through the universe, on top of the expansion toward something unseen. The Great Attractor entered human knowledge in 1987 within the lifetime of many people listening tonight. And Laniakea, the Great Basin we belong to, the immense heaven, was only named and mapped in 2014. The Dipole Repeller, the void pushing at our backs, was only proposed in 2017. The full shape of our cosmic fall, the picture we have drawn together tonight, is younger than many of the devices in your home. We are among the first generations of human beings who have ever known where we are going, who have ever been able to point to the southern sky and say, "That way, we are falling that way," and name the things that pull us. Every person who lived and died before the late 20th century went to their rest, never knowing the great motion that carried them. Pattern interrupt. Sit for a moment with how lucky that makes us, in a quiet way. For tens of thousands of years, human beings looked up at the same southern stars toward the very direction of our fall, and saw only patterns, only constellations, only the fixed and turning sky. The great current was carrying them all along, exactly as it carries us, and they could not know it. We can. We happen to be alive in the brief slice of history when this became knowable, when the instruments grew sharp enough, and the ideas clear enough to reveal the motion we are all part of. It is one of the youngest pieces of knowledge our species possesses, and you are holding it tonight, lying still while the galaxy falls. No one expects that so much of what we know about our place in the universe was discovered so recently, within a single human lifetime, after tens of thousands of years of not knowing. No one predicts that the map of our great fall would still be getting drawn in our own era. The basin named in 2014, the Great Push found in 2017. And absolutely no one anticipates the strange privilege of the timing that of all the generations of humans who have ever gazed at the southern sky, ours is among the first to know what lies behind it and which way we are quietly, endlessly falling. It is not. And the way we found that out is one of the most beautiful pieces of detective work in the history of science, because it came from listening to the faintest sound in all of creation, the cooling whisper of the Big Bang itself. Let me tell you what we are actually made part of, because the word galaxy does a lot of hiding. Picture the Milky Way not as a scatter of stars, but as a single object, a vast flattened spiral of light 100,000 light years across, turning slowly in the dark. That whole object, intact, is what is moving. Not the stars within it sliding around, but the entire thing, bodily, like a single leaf. carried on a current. And the current is not random. It has a direction, fixed and steady, pointing toward a particular patch of sky in the direction of the southern constellations of Centaurus and Norma. Everything we are is drifting that way together and has been since before there were oceans on the earth. The speed is hard to hold in the mind, so let us anchor it. More than 1 million miles per hour. About 1.3 million miles per hour, to put a number on it, give or take. At that speed, you would cross the entire distance from the Earth to the Moon in about 11 minutes. You would circle the whole planet in under 2 minutes. And you are doing it right now, lying still, feeling nothing, because there is no wind out there to feel and nothing nearby to measure yourself against. The motion is real, constant, and utterly silent. The most enormous journey of your life is the one you will never sense. Now, let's begin with a question that may have been quietly nagging at you all through tonight, and it is a good one, so let us answer it properly. If we are truly moving at over 1 million miles an hour, why can we not feel it? Why does nothing rattle, nothing blur, nothing press against us? How can the most enormous motion of our lives be completely undetectable to our bodies? The answer is one of the oldest and deepest truths in physics, older than the discovery of the Great Attractor by more than 3 centuries. It was first understood clearly by Galileo 400 years ago, and he explained it with a beautiful thought experiment about a ship. Imagine you are below deck in the cabin of a great sailing ship, moving smoothly across a calm sea, with no windows to see out. Galileo pointed out that there is no experiment you could do inside that sealed cabin, none at all, that would tell you whether the ship was gliding along at a steady speed or sitting perfectly still in harbour. Drop a ball and it falls straight down just the same. Pour water and it pours just the same. A fly buzzes about the cabin exactly as it would at rest. Smooth, steady motion is completely undetectable from the inside. Only changes in motion, speeding up, slowing down, turning, can be felt. Steady motion itself feels exactly like rest. This is why you feel nothing of the galaxy's great fall. The motion is smooth and steady, unchanging in speed and direction over any span of time a human being could notice. And crucially, everything around you shares it perfectly. The earth, the air, your bed, your body, your cup of water on the table, all of it is moving at that same 1,000,000+ miles an hour in the same direction, together, in flawless unison. There is no part of your world being left behind, nothing to lag or press or rattle, because there is no difference in motion anywhere in your surroundings to feel. You and everything you can touch are gliding through the cosmos in perfect step, and perfect shared motion is indistinguishable, in every possible way, from perfect stillness. It is the same reason you do not feel the earth spinning, though at the equator that spin carries you at around 1,000 miles an hour. It is the same reason you do not feel the earth's orbit around the sun, which moves you at 67,000 miles an hour. It is the same reason a passenger asleep on a smooth, high-speed train, shades drawn, cannot tell they are moving at all. The body senses changes, jolts, accelerations, turns. It cannot sense steady motion, no matter how fast, because steady motion has no internal signature, nothing to detect. The faster you go, as long as you go smoothly, the more it feels like exactly nothing. Pattern interrupt. There is a deep peace available in this fact, and it is worth taking into sleep. The universe does not ask you to brace against its great motions. It does not require you to hold on. The spin of the Earth, the orbit around the sun's long circuit of the galaxy's vast fall toward the Great Attractor, all of these enormous motions are carrying you this very moment, and every one of them is so smooth, so perfectly shared by everything around you, that they arrive in your body as stillness. The cosmos moves you tremendously and lets you rest completely at the very same time, and there is no contradiction in it at all. No one expects that the way to feel 1,000,000 miles an hour is to feel nothing whatsoever, but that is exactly the law of it, understood since Galileo's ship. No one predicts that the most enormous motions in existence would be precisely the ones the body cannot sense, hidden by their own smoothness and their own perfect sharing. And absolutely no one anticipates how kind that turns out to be, that you can be flung through the universe faster than any machine humanity has ever built and still lie here, undisturbed, perfectly at rest, carried and unbothered all at once. So how could anyone possibly know? If you cannot feel it, if there is no landmark out there in the dark to clock yourself against, how do you measure the speed of an entire galaxy through empty space? That question has a genuinely astonishing answer, and it is where our fall properly begins. The answer came from the oldest light there is. Everywhere you look in the universe, in every direction, there is a faint glow. You cannot see it with your eyes, but it is there. A whisper of microwave radiation filling all of space, and it is the single most important light ever discovered. It is the afterglow of the Big Bang itself, the heat of the universe's fiery birth, stretched and cooled over nearly 14 billion years into a cold, dim hum. Astronomers call it the cosmic microwave background, and it is, in a sense, a photograph of the universe when it was only 380,000 years old, long before there were any stars or galaxies at all. It is the wall at the edge of the observable, the furthest back we can ever see. And here is the thing that matters for tonight. That glow is almost perfectly even. It comes at us from every direction with almost exactly the same faint temperature, the same gentle hum, whether you look up or down or left or right. The universe on the largest scale is astonishingly smooth. So when astronomers built instruments delicate enough to measure that glow precisely, they expected to find it the same everywhere. It was not, quite. There was one pattern, one single large deviation, and it was the most important imperfection ever measured. In one direction of the sky, the glow was very slightly warmer. In the exact opposite direction, it was very slightly cooler. Warmer ahead, cooler behind. And that pattern, that one warm spot and one cool spot on opposite sides of the sky, has a name. It is called the dipole, and what it means is simple and profound. We are moving. Think about what happens when you move through something that fills all of space. The light coming from the direction you are heading gets compressed, squeezed, shifted slightly warmer and bluer, just as the pitch of a siren rises as it races toward you. The light coming from behind the direction you are leaving gets stretched, shifted cooler and redder, just as the siren drops in pitch as it speeds away. The ancient glow of the Big Bang is the one thing in the universe that sits still enough and fills space evenly enough to serve as a backdrop you can measure yourself against. It is the closest thing there is to a fixed stage. And against that stage, the warm spot ahead and the cool spot behind reveal our motion through the cosmos with beautiful precision. When astronomers measured the size of that warm, cool pattern, they could read our speed directly off of it. The way you could read a car's speed off the exact amount the siren's pitch had shifted, the answer, once they accounted for the Earth's spin and orbit and the Sun's path around the galaxy, was that the entire Milky Way is moving at about 1.3 million miles per hour relative to that ancient light, relative to the universe itself. And it is heading toward that patch of sky in the south, toward Centaurus, toward the constellation Norma, toward something. By the end of tonight, you are going to understand one more open question worth sitting with before we turn towards sleep, because it is live right now, unresolved, the kind of puzzle that keeps cosmologists up at night, and it touches the very measurement at the heart of tonight's story. Remember how we found our speed. The dipole, the warm spot ahead and cool spot behind in the ancient glow of the Big Bang, told us we are moving at about 1.3 million miles an hour toward the south. That is the standard, well-established result. But here is the thing. If that motion is real, and it surely is, then it should leave the same fingerprint, not only on the ancient background glow, but on everything else in the distant universe too. In particular, our motion should make the distant galaxies and quasars appear very slightly bunched up in the direction we are heading and slightly thinned out behind us. The same dipole pattern, the same warm and cool, but written in the counts of distant objects, rather than in the temperature of the background. And crucially, both measurements should give the same answer, the same speed, the same direction. They are two ways of measuring the one motion. In recent years, several teams have actually done this. They counted enormous numbers of distant radio galaxies and quasars across the whole sky, looking for that subtle bunching, that dipole in the counts of distant objects. And they found a dipole pointing in roughly the right direction, which is reassuring, but the size of it came out wrong. The dipole measured from the distant galaxies appeared to be about twice as large as the one measured from the ancient background glow, as though, by that method, we were moving much faster than the background says we are. Two ways of measuring the same motion, and they disagree, not by a little, but by a factor that should not happen if our simple picture is correct. Now, the careful, honest thing to say is that this is unsettled and may yet be resolved in a perfectly ordinary way. Counting distant galaxies across the whole sky is fiendishly difficult, riddled with subtle biases, and it is entirely possible that some unrecognized error in the counts is inflating the result, and that better data will bring the two measurements back into agreement. Many cosmologists expect exactly that. But it is also possible, just possible, that the disagreement is real and that it is telling us something we do not understand about our motion, or about the distribution of matter on the largest scales, or about some assumption buried so deep in our picture of the universe that we have never thought to question it. No one yet knows which it will turn out to be. Pattern interrupt. I share this not to unsettle you, but because it is the truest possible note to end the science on. The story of our great fall is not a closed book, finished and shelved. It is a living science with its established triumphs, the Great Attractor, Laniakea, the measured speed of our fall, and also its open edges, its genuine puzzles, its measurements that do not quite agree and wait right now for the next generation of instruments to resolve them. We have learned an astonishing amount about the great motion that carries us. And there is still more we do not understand, sitting at the very heart of it, in the one number we thought we knew best. No one expects the very measurement that revealed our motion to harbour a fresh puzzle decades later. Two ways of clocking our speed that stubbornly disagree. No one predicts which open questions will dissolve into ordinary error and which will crack open into genuine discovery. And the only honest answer, tonight, is that we will have to wait and see. And absolutely no one anticipates how good it feels in the end to rest inside a science still in motion, still curious, still willing to say of the thing it knows best, there is something here we have not yet understood, and we are still, patiently, falling toward the answer. Tonight we're going to slow down and sit with that measurement because the story of how we actually pin down our speed is worth the telling, and it spans decades. The dipole, that warm spot ahead and cool spot behind in the ancient glow, was first hinted at in the late 1960s and 1970s, when physicists flew sensitive microwave detectors high into the atmosphere aboard balloons and even repurposed U-2 spy planes, lifting their instruments above as much of the Earth's interfering air as they could. From those high, cold flights came the first real measurement of the dipole, the first proof that we were moving against the background of the Big Bang. It was a stunning result, but the instruments were crude by later standards, and the exact speed and direction stayed fuzzy. Then, in 1989, NASA launched a satellite called COBE, the Cosmic Background Explorer, designed to map that ancient glow from orbit with a precision no balloon could match. COBE confirmed the dipole with beautiful clarity. Later satellites, WMAP in the 2000s and the European Planck mission in the 2010s, refined it further still, until the measurement became one of the most precise in all of cosmology. Today, we know our speed against the cosmic background to within a small fraction, about 1.3 million miles per hour, and we know the direction with great confidence toward a specific point in the southern sky. Here is a detail that makes the whole thing feel real. The instruments are so sensitive that they can pick out the separate contributions to our motion and add them up. The Earth's spin, the Earth's orbit around the Sun, which alone moves us about 67,000 miles per hour and which shifts the measured dipole slightly back and forth over the course of a year as we swing around the Sun's great orbit around the center of the galaxy, nearly 500,000 miles per hour. And then, underneath all of those, the deep motion of the galaxy itself through space. Astronomers can subtract off the local motions, the spin and the orbits, the way you might subtract the rocking of a boat to find the true current of the river beneath it. And what remains, when all the local motions are removed, is the galaxy's own fall, steady and silent, toward the Great Attractor. No one expects that a faint imperfection in the oldest light in the universe could be decoded so precisely that we can read off the speed of our planet, our sun, and our entire galaxy separately, like layers in a sediment. But that is exactly what the great background experiments achieved. The afterglow of creation turned out to be the most honest speedometer ever built, and it has been quietly clocking our fall since before any of us were born. No one expects the universe to come with a speedometer built into it, but in a sense it does, and that speedometer is the oldest light in existence. No one predicts, on first learning, that the cosmic background is almost perfectly smooth, that its one great imperfection would turn out to be a portrait of our own motion. And absolutely no one anticipates how unsettling it is to discover that you have been travelling at over 1,000,000 miles an hour your whole life in a direction you cannot point to, toward a destination you cannot see. Tonight, we're going to bring all of this back to something you could almost do yourself on a clear, dark night, if you were in the right place on the Earth. Let us actually find the direction of our fall in the sky. The Great Attractor, lies in the direction of two southern constellations, Centaurus and Norma. Centaurus is a large, bright constellation of the southern sky, home to some of the most familiar sights of the southern hemisphere, including the pointer stars near the Southern Cross and the closest star system to our own, Alpha Centauri. Norma is fainter and more obscure, a small dim constellation tucked into the rich star fields of the southern Milky Way, named, rather sweetly, for a carpenter's square, a right-angle ruler. To see this part of the sky well, you would need to be in the southern hemisphere, or at least far enough south, and you would look toward that bright, dense band of the Milky Way where it runs through Centaurus and Norma and Scorpius, the crowded heart of the southern sky. And here is the poignant thing. If you stood under that southern sky tonight and looked toward Norma, toward the exact direction our entire galaxy is falling, you would see with your own eyes only the bright band of the Milky Way, the near stars of our own galaxy, glowing thick across that part of the heavens. You would not see the Great Attractor. You could not. That very brightness, the dense glow of our galaxy's own stars and dust, is the Zone of Avoidance, the veil that hides the great mass behind it. You would be looking directly at the thing pulling our entire galaxy across the universe, and you would see nothing but the curtain drawn in front of it, the luminous body of home standing squarely between you and your destination. There is something almost unbearably fitting in that. The direction of our great fall is not hidden in some obscure, hard-to-find corner of the sky. It is right there, in one of the richest and most beautiful regions of the southern Milky Way, a part of the sky that people have gazed at and loved for as long as there have been people in the southern world. The ancestors of every southern culture looked toward Norma and Centaurus, toward the very direction of our cosmic fall, and saw the bright river of the Milky Way, and told stories about it, and never knew that they were looking along the path of the greatest motion they were part of. The destination was always in plain sight and always hidden, both at once. Pattern interrupt. So the next time you see a photograph of the southern Milky Way, that gorgeous, dense band of light through Centaurus and Scorpius, or if you are ever lucky enough to stand beneath it yourself, you will know something the photograph does not show. Somewhere behind that bright glow, hidden in its light, more than 150 million light-years away, lies the great crowded valley toward which you and the Earth and the Sun and every star around you are endlessly falling. You will be looking straight at it and straight past it in the same gaze. The brightest, most beautiful part of our sky is also the doorway we are falling through and cannot see. No one expects the direction of their cosmic fall to lie in plain view in one of the loveliest regions of the night sky, hidden only by its own brightness. No one predicts that you could point your finger at the Great Attractor on any clear southern night and see nothing but the glowing veil of home in the way. And absolutely no one anticipates how the whole long mystery comes down to this simple human fact that the thing pulling us is not far off in some unreachable dark, but right there behind the familiar band of the Milky Way, close enough to point to, bright enough to hide. Because that was the next question, and it was a hard one. We knew our speed. We knew our direction. Something was pulling us gravitationally toward that patch of southern sky. But when astronomers turned their telescopes that way to see what it was, to find the great mass that must be doing the pulling, they ran into a wall. And the wall was us. The thing pulling our galaxy lay in almost exactly the direction where our own galaxy blocks the view. We had found the pull. We could not find the puller. And so for a while it became one of the great mysteries in astronomy, a powerful, invisible something drawing in everything around us, hiding in the one blind spot we cannot easily see past. Before we get started, let us clear away a few common misunderstandings about the Great Attractor, because it is the kind of subject that grows strange rumours, and the truth is more interesting than any of them. The first misunderstanding is that the Great Attractor is a black hole, or some single exotic object, a great cosmic drain sucking everything in. It is not. There is nothing exotic about it at all. The Great Attractor is simply a region where many galaxies and several large clusters happen to gather. An ordinary, if very large, concentration of perfectly ordinary matter, galaxies and gas, and the dark matter that accompanies them. Its pull is just gravity, the same gravity that holds you to your bed, summed over an enormous amount of mass. There is no special force, no mystery substance, no abyss. It is a crowded valley, not a plug hole. The second misunderstanding is that we are being pulled in to be destroyed, that the Great Attractor is dragging us towards some violent end. We have already seen why this is wrong, but it is worth saying plainly. We are not going to arrive. The expansion of the universe is carrying the Great Attractor away from us faster than our fall can close the gap. Far from rushing toward a doom, we are in a slow reach towards something we will never touch, a fall that grows gentler and more futile with every passing age as the cosmos stretches between us. There is no collision in our future with the Great Attractor. There is only the long, slow, unfinished lean. The third misunderstanding is that this motion is somehow dangerous or detectable in daily life, that moving at over 1,000,000 miles an hour must have some effect we should worry about. It does not. Steady motion, no matter how fast, feels like nothing at all, because there is nothing to feel it against. You are moving at over 1,000,000 miles an hour right now, and your tea is not sliding off the table, because the table and the tea and the Earth and the whole galaxy are all moving together, perfectly in step. Smooth motion is indistinguishable from rest. This is one of the oldest truths in physics, and it is why the most enormous journey of your existence is also the most peaceful. The fourth misunderstanding is that the Great Attractor is the center of the universe, or that our falling toward it means we sit at some special edge. There is no center of the universe. Every galaxy, everywhere, is being pulled by the particular arrangement of mass and emptiness around it, each one falling its own way toward its own local valleys. Our fall toward the Great Attractor is our local story, not a cosmic one. A galaxy on the far side of Shapley would feel quite different pulls toward quite different places. We are not special. We are simply somewhere, and, like everywhere, our somewhere has its own slope. No one expects the truth to be so calm after the dramatic name. The Great Attractor sounds like a monster, and it is, in the end, just a large, crowded region of ordinary galaxies, reaching for us with ordinary gravity across a gap that the expanding universe will never let us cross. No one predicts that the most enormous pull we are subject to would be, in every practical sense, completely harmless. And absolutely no one anticipates how much gentler the real universe is than its frightening names suggest, how a thing called the Great Attractor turns out to be a quiet valley we are forever, peacefully, falling toward, but never into. By the end of tonight, you are going to understand both what that hidden mass turned out to be and why it remains so stubbornly hard to look at. But to get there, we have to go back to the 1970s and 1980s to a small group of astronomers who first realized that we and thousands of galaxies around us were all streaming together toward the same unseen place, and who gave the mystery the name it still carries. In the early 1980s, a group of 7 astronomers set out to do something that sounds modest and turned out to be revolutionary. They wanted to map how galaxies near us are moving. This is harder than it sounds, and the reason is the expansion of the universe. Almost every galaxy is rushing away from us, carried apart by the steady stretching of space itself, and the farther away a galaxy is, the faster it recedes. This is one of the most reliable patterns in all of astronomy. So, if you measure how fast a galaxy is moving away, you can estimate how far away it is. But that only works if the expansion is the only thing moving the galaxy. And the 7 astronomers wanted to know whether it was. They wanted to find the extra motions, the local drifts, the places where galaxies were moving not just with the expansion but on top of it, pulled by the gravity of their neighbours. So they measured, painstakingly, the true distances to hundreds of galaxies, using the properties of the galaxies themselves rather than just their recession speed, and then they compared those true distances to how fast each galaxy appeared to be moving. The difference between the two, between how fast a galaxy should be receding and how fast it actually was, would reveal the hidden tug of gravity, the streaming motions underneath the expansion. Now, let's begin with a fair challenge. We keep saying that astronomers measured the true distances to thousands of galaxies independently of their speed. And you might reasonably wonder how on earth that is possible. You cannot stretch a tape measure to a galaxy. You cannot bounce a signal off one and wait for the echo. So how do you know how far away something is when it is millions of light years across the void? The answer is one of the quiet triumphs of astronomy, and it turns on a beautiful trick. The method the 7 samurai relied on is called the Tully-Fisher relation, discovered in the 1970s by the same Brent Tully, working with Richard Fisher. They found that for spiral galaxies there is a tight connection between how fast a galaxy spins and how bright it truly is. Bigger, more massive galaxies hold more stars and shine more brightly, and they also spin faster, because more mass means stronger gravity, means faster rotation to hold together. So, if you measure how fast a galaxy is spinning, which you can do from the way its light is shifted on the approaching and receding sides, the Tully-Fisher relation tells you how bright that galaxy truly is. Its real, intrinsic luminosity. And here is where the distance falls out. Once you know how bright a galaxy truly is, and you compare that to how bright it actually appears in your telescope, the difference tells you how far away it must be. It is the same logic as a candle flame. If you know a candle gives off a certain amount of light and you see it looking very dim, you know it must be far away, and you can even say roughly how far, because light fades in a precise and predictable way with distance. A galaxy whose true brightness you know becomes a kind of standard candle, and its apparent dimness becomes a ruler. Measure the spin, get the true brightness, compare to the apparent brightness, and read off the distance, all without ever using the galaxy's recession speed at all. This is what made the whole discovery possible. With the Tully-Fisher relation in hand, astronomers could measure the true distance to a spiral galaxy by one method, its spin and brightness, and its total speed by another, the shift of its light. 2 independent numbers for each galaxy. Subtract the expansion that the distance predicts, and the leftover peculiar velocity emerges, the local drift. the streaming toward the Great Attractor. Without a reliable way to measure distance independently of speed, the Great Attractor would have stayed forever invisible, its pull tangled hopelessly inside the general expansion. The Tully-Fisher relation untangled it. There are other rungs on this ladder of distance, other standard candles for other kinds of galaxies, exploding stars of a particular type that always shine with nearly the same true brightness, and methods based on the way the surface of a galaxy looks grainy or smooth depending on how far away it is. Astronomers combine them all, cross-checking one against another, building ever more reliable maps of how far the galaxies truly are. And every flow map of the Great Attractor, every measurement of our Great Fall, rests on this foundation, the patient, clever business of measuring the unreachable. No one expects that the spin of a galaxy could tell you how far away it is, but it can, because nature tied a galaxy's brightness to its rotation, and brightness, compared to appearance, is a ruler. No one predicts that the entire discovery of our cosmic fall would rest on a relationship between how fast galaxies turn and how brightly they shine. And absolutely no one anticipates how much of cosmology comes down to this single deep problem, measuring the distance to things you can never approach, solved not with one method but with a whole ladder of them, each rung checking the last. What they found astonished them. The galaxies were not drifting randomly. Across an enormous region of space, hundreds of galaxies, our own included, were all streaming in the same direction, toward the same patch of sky, the one in Centaurus and Norma. It was as if they had been studying the surface of a vast river and discovered that everything, for hundreds of millions of light years in every direction, was flowing toward the same waterfall. Something out there was pulling not just us, but a whole enormous neighborhood of galaxies toward a single point. The 7 astronomers, who became known, half affectionately, as the 7 Samurai, published their findings in 1987, and one of them, Alan Dressler, gave the unseen mass its name. He called it the Great Attractor. It was a name that admitted what they did not know, not the Great Cluster, not the Great Galaxy, because they could not see what was there, just the Great Attractor, the great thing that attracts, a placeholder for a mystery. And it was a real mystery, because when they worked out how much mass it would take to pull such a vast region of the universe around, the number was staggering. To draw in everything they were seeing, the Great Attractor would need to be something like the mass of tens of thousands of galaxies, concentrated in one region of space about 150 million light-years away. Tens of thousands of galaxies worth of gravity, all in one place, reaching out across the void to grasp our entire corner of the cosmos. And it sat almost exactly behind the disk of our own Milky Way, in the worst possible place to look. By the end of tonight, you are going to understand a hidden ingredient in this whole story that we have only mentioned in passing. And it deserves its own moment, because without it, none of the numbers work. When astronomers add up all the mass they can see in the Great Attractor region, all the galaxies, all the hot gas in the clusters, everything that gives off light of any kind, they find it is not nearly enough to produce the pull we feel. Expectation, the galaxies and glowing gas we can see should account for the pull. Reality, the visible matter falls short by a great deal. Something else is there providing most of the gravity, and it gives off no light at all. That something is dark matter, and it is not a small correction. It is the majority of all the matter in the universe. For every pound of ordinary matter, the kind that makes stars and planets and people, there are about 5 pounds of this dark, invisible material spread through every galaxy and every cluster, forming a vast unseen scaffolding on which all the bright structures hang. We cannot see it directly. It does not shine, does not absorb light, does not interact with ordinary matter in any way we can easily catch. We know it is there only by its gravity, by the way it bends the paths of stars and galaxies, and light itself by the way it holds clusters together that would otherwise fly apart. The Great Attractor, then, is mostly dark. The Norma Cluster and the other clusters gathered at the bottom of our basin are wrapped in enormous halos of dark matter, far outweighing their visible galaxies, and it is that dark mass, mostly, that does the pulling. When we say we are falling toward the Great Attractor, we are falling toward a great concentration of something we have never seen and do not understand, identified only by the force it exerts. The thing drawing our entire galaxy across the universe is, in its bulk, a mystery within the mystery. This is part of why the Great Attractor was so confounding at first. The 7 samurai measured the pull and tried to find enough visible mass to explain it, and could not, and for a while it seemed there must be some enormous, hidden cluster of galaxies lurking behind the Zone of Avoidance to make up the difference. But the deeper answer is that even the galaxies we can now see in that region are only the visible tips of something far more massive, vast halos of dark matter cradling them, supplying the gravity that the starlight alone could never account for. The pull was never going to be explained by the things that shine. Most of the universe's gravity comes from the things that do not. No one expects that the majority of the mass pulling on our galaxy would be a substance no one has ever directly seen or identified. No one predicts that when you finally pierce the veil and look at the Great Attractor, the galaxies you find there will still be only a fraction of what is truly pulling you, the rest of it dark, silent, and everywhere. And absolutely no one anticipates how much of the universe runs on the unseen, how the great currents that carry us were charted by a force we feel perfectly well, and a substance we have never once held to the light. No one expects to discover that they live downstream of an invisible waterfall, but that is essentially what the 7 samurai found. No one predicts that the orderly recession of the galaxies, the famous expansion of the universe, would have hidden underneath it a great secret current, a streaming of thousands of galaxies toward a single unseen mass. And absolutely no one anticipates that the thing pulling on everything we are would turn out to hide in the one direction our own galaxy makes nearly impossible to see. Here is the picture to hold as we fall. Expectation: the galaxies near us drift apart smoothly, evenly, each one carried away by the expansion, an orderly and quiet retreat. Reality: beneath that orderly retreat runs a hidden river, and we are in it, and the whole neighborhood of galaxies is being drawn together toward a great mass we cannot see, falling sideways across the expansion toward the constellation Norma at over 1,000,000 miles an hour. Tonight, we're going to go a little deeper into the idea at the very heart of how all of this was discovered, because it is subtle. And once you see it clearly, the whole story snaps into focus. It is the difference between 2 kinds of motion, and astronomers have names for both. The first kind is the expansion of the universe itself. Space is stretching, everywhere, all the time, and this stretching carries the galaxies apart from one another. A galaxy twice as far away recedes twice as fast, a galaxy 3 times as far recedes 3 times as fast, and so on, in a clean and simple proportion that astronomers call the Hubble flow, after Edwin Hubble, who first measured it. The Hubble flow is the orderly, universal retreat of the galaxies, the background rhythm of the expanding cosmos. If the Hubble flow were the only thing moving the galaxies, then measuring how fast a galaxy recedes would tell you exactly how far away it is, with no ambiguity at all. But there is a second kind of motion, and it is the one that matters for tonight. On top of the smooth Hubble flow, each galaxy also moves a little on its own, tugged by the gravity of its neighbours, drawn toward nearby masses, pushed from nearby voids. Astronomers call this extra local motion the peculiar velocity, using the old meaning of peculiar, which is to say particular, belonging to that one galaxy. The peculiar velocity is the galaxy's own private drift, separate from the universal expansion, and it is the fingerprint of the local gravitational landscape. It is the part of a galaxy's motion that reveals what is pulling on it. Here is the difficulty and the genius of the solution. When you look at a single galaxy and measure how fast it is moving away from you, you measure the sum of both motions at once, the Hubble flow plus the peculiar velocity, blended together into a single number. You cannot, from that one number alone, separate them. The expansion and the local drift are tangled. So how did anyone ever pull them apart? The answer is that you must measure the true distance to each galaxy independently, by some method that does not rely on its speed at all. Then you can calculate how fast the Hubble flow alone should be carrying it away. Based purely on that distance and whatever is left over, the difference between the speed you actually measure and the speed the expansion predicts is the peculiar velocity, the pure signal of local gravity, the streaming we have been chasing all night. This is exactly what the Seven Samurai did, and what every flow mapping survey since has done. Measure the true distances, subtract the expected Hubble flow, and read off the peculiar velocities, the hidden drifts. And when they did this for galaxy after galaxy across a huge region, the peculiar velocities did not point every which way. They lined up, all streaming together toward the Great Attractor. The local drift of our entire region laid bare once the expansion was subtracted was a single great current toward the south. No one expects that two completely different motions could be hiding inside one measured number. The universal expansion and the private local fall blended into a single speed. No one predicts that separating them would require measuring the true distance to thousands of galaxies by entirely independent means, a labor of years. And absolutely no one anticipates how clean the result would be once the expansion was peeled away, how the leftover motions, freed of the Hubble flow, would all point the same way, like iron filings suddenly snapping into alignment around a hidden magnet in the south. But to understand what the Great Attractor actually is and why it stayed hidden for so long, we have to look directly at the thing standing in our way. We have to understand the strange region of the sky that astronomers call, with a kind of poetry that is rare in science, the Zone of Avoidance. If you have ever been somewhere truly dark, far from any city, and looked up on a clear night, you have seen the Milky Way. Not the galaxy as a whole, which we are inside of, but a pale band of light arching across the sky, soft and milky, which is how it got its name. That band is the combined glow of hundreds of billions of distant stars in the flat disk of our galaxy. Seen edge-on from our position inside it, it is beautiful. And for astronomers trying to see past it, it is a catastrophe. Because that band of light is not just stars, it is also gas, and above all, it is dust. Vast clouds of fine, dark dust, strung through the disk of the galaxy, that soak up light the way fog soaks up the glow of a distant streetlight. When you look out at the universe in any direction away from that band, the dust is thin, and you can see for billions of light years all the way to the edge of the observable universe. But when you try to look through the band itself, through the crowded, dusty, star-choked plane of our own galaxy, the view closes down. The dust absorbs the light of whatever lies beyond. The crowd of nearby stars drowns out the faint smudges of distant galaxies. It is like trying to see a candle on a far hillside through a bonfire 3 feet in front of your face. By the end of tonight, you are going to understand why we say most of the mass pulling us is dark, an unseen substance we know only by its gravity, and you would be right to want some proof of so strange a claim. How can anyone be sure that this invisible matter is real and not simply a sign that we misunderstand gravity itself? It is a fair challenge, and the answer is one of the most elegant observations in modern astronomy. It involves watching 2 great galaxy clusters collide. A galaxy cluster is made of 3 things in very different amounts. There are the galaxies themselves, the bright swarms of stars, but they are actually a small part of the total. There is a vast amount of hot gas, far more mass than all the stars, filling the space between the galaxies and glowing in X-rays. And then there is the dark matter, more massive than the gas and the galaxies combined, the great unseen bulk of the cluster. In an ordinary settled cluster, all 3 are mixed together in the same place, and you cannot easily tell them apart. But a collision separates them, and that is the key. There is a famous object called the bullet cluster, where 2 great clusters of galaxies have smashed through each other. When astronomers studied it, they found something revealing. The hot gas, the ordinary visible matter, the bulk of the normal stuff, behaved as you would expect when 2 clouds collide. It slowed down, piled up, heated further, and lagged behind in the middle of the wreck, dragged to a halt by the impact, glowing brightly in X-rays right where the crash occurred. But the mass, the real gravitational mass of the clusters, measured by the way the whole scene bends the light of more distant galaxies behind it, was not in the middle with the gas. It had passed straight through and sailed on ahead, separated cleanly from the visible matter, sitting out where the galaxies had gone, not where the gas had piled up. This is exactly what you would expect if most of the mass is dark matter that barely interacts with anything. The dark matter of each cluster, feeling almost nothing as the clusters passed through each other, would simply glide on through, while the ordinary gas, which does interact, would slam together and stop. And so the collision pried the dark matter loose from the visible gas and let us see, for the first time, that the mass and the visible matter are genuinely 2 different things, sitting in 2 different places. The gravity is out ahead, where the unseen dark matter went. The glowing gas is stuck behind in the middle. You can see the proof in the separation itself. The bullet cluster is, for many astronomers, the single most convincing piece of evidence that dark matter is real, a true substance and not merely a flaw in our theory of gravity. Because if it were only that we misunderstand gravity, the extra pull should sit where the visible matter is, with the gas in the middle. Instead, it sits out ahead, with nothing visible there at all, exactly where invisible matter should have coasted. The dark mass announced itself by leaving the light behind. No one expects to be able to see invisible matter, but in a sense the bullet cluster lets us by catching it in the act of separating from everything that shines. No one predicts that a collision between 2 great clusters would be the thing to prove the unseen substance real by prying it loose from the visible wreck. And absolutely no one anticipates how much of the universe's gravity, the very gravity drawing us toward the Great Attractor tonight, comes from this dark and silent stuff, proven real not by any light it gives, but by the unmistakable place it went when two clusters crashed. Astronomers call this blocked band the Zone of Avoidance, because it is the region of the sky that the galaxies appear to avoid. Of course, they do not really avoid it. The galaxies are out there behind the band, just as thick as anywhere else. We simply cannot see them because our own galaxy is in the way. For most of the history of astronomy, the Zone of Avoidance was a blank stripe across our maps of the universe, a place where the data simply stopped, covering something like a fifth of the entire sky, a fifth of the universe hidden behind the brightness of home. And here is the cruelty of it, the thing that turned a nuisance into a profound mystery. The Great Attractor, the unseen mass pulling our entire region of space toward it, sits almost squarely behind the Zone of Avoidance. Of all the directions it could have been, it lay in the one direction we are least able to see. The very thing astronomers most wanted to look at was hidden behind the very thing most in the way. It was as though the universe had placed its greatest nearby secret in its own blind spot, deliberately, just out of reach. So for years the Great Attractor stayed a shadow. We could measure its pull with great confidence. We could feel, in the streaming motions of thousands of galaxies, the unmistakable grip of an enormous mass. But we could not see what was doing the grasping. The pull was certain. The puller was invisible. What changed was that astronomers found new ways to see. The dust that blocks ordinary visible light is far less able to block other kinds. Infrared light, the light of heat, slips through the dust much more easily, and as infrared telescopes improved through the 1990s, astronomers could begin to peer into the Zone of Avoidance for the first time. Radio waves passed through the dust almost untouched, and radio surveys began mapping the hidden galaxies by the faint hiss of their hydrogen gas. X-rays, the light of the hottest matter in the universe, revealed the superheated gas that pools in the hearts of great galaxy clusters, glowing right through the obscuring band. One by one, these new eyes began to lift the veil. Tonight, we're going to spend a few minutes on exactly how astronomers learn to see through the Zone of Avoidance, because the techniques are clever and the story is one of patient ingenuity over many years. The problem, remember, is dust. Fine dark grains strung through the disk of our galaxy, soaking up visible light, dimming and reddening everything behind them until the distant galaxies simply vanish from view. For ordinary telescopes, the kind that gather the same light your eyes use, the galactic plane is very nearly a brick wall. But the universe sends us light in many forms, and dust is not equally good at blocking all of them. The first great breakthrough was infrared light, the light of heat, with wavelengths longer than the eye can see. Dust grains are small, and a fundamental rule of physics is that small things block short waves far better than long ones. Visible light has short waves, and the dust catches it easily. Infrared light has longer waves that slip past the grains far more readily, the way long ocean swells roll past a piling that would shatter short, choppy waves. So when astronomers built infrared surveys, mapping the sky in the light of heat, they could suddenly see galaxies that were completely invisible to ordinary telescopes, glowing right through the dusty band. Surveys like the 2-micron All Sky Survey in the early 2000s mapped huge numbers of these hidden galaxies for the first time. Radio waves did even better. Radio has waves so long that the dust is almost completely transparent to them, and galaxies full of hydrogen gas give off a particular radio signal. A faint hiss, at a specific wavelength that radio telescopes can detect right through the galactic plane. By tuning to that hydrogen signal, astronomers could count and map and measure the speeds of galaxies behind the zone of avoidance that no optical telescope would ever catch. The hidden galaxies announce themselves not in light but in the soft radio whisper of their gas. And X-rays added the final piece. The great clusters of galaxies, like the Norma Cluster at the heart of the Great Attractor, hold vast reservoirs of gas heated to tens of millions of degrees, so hot that it glows not in visible light, but in X-rays, the light of the most violent and energetic processes in the universe. X-ray telescopes in orbit above the Earth's atmosphere could detect that hot gas pooling in the hearts of the hidden clusters, revealing the great masses behind the band by their fierce internal glow. Where the optical sky showed only blankness, the X-ray sky showed the buried giants shining through. Piece by piece, survey by survey, decade by decade, these different kinds of light filled in the blank stripe across our maps. The zone of avoidance has never been fully cleared, and even now there remains a narrow strip right along the very centre of the galactic plane, the most crowded and dusty part, where our view is still poor and where, very possibly, more massive structures still hide undiscovered. But the Great Veil has been mostly lifted, and the Great Attractor, once a pure mystery, now has a face, a gathering of clusters in the once hidden south, mapped in heat and radio and X-ray light. No one expects that the way to see a thing hidden behind dust is simply to look in a different kind of light, but that is exactly the lesson. No one predicts that galaxies invisible to every optical telescope ever built would shine clearly in radio or infrared or X-ray, as though they had been waiting all along for us to open the right eye. And absolutely no one anticipates that even now, with all our instruments, a thin band of the universe remains genuinely unmapped right along the heart of our own galaxy, still keeping whatever secrets lie directly behind the brightest part of home, and slowly, behind the zone of avoidance, in the direction of all that pulling, a shape emerged from the dark. When the new eyes finally pierced the zone of avoidance and looked toward the heart of the Great Attractor, they found, sitting almost exactly where the pull pointed, an enormous cluster of galaxies. It has a catalogue name, Able 3627, but astronomers more often call it the Norma Cluster, after the faint southern constellation it hides behind. For a long time, the Norma Cluster was almost completely unknown, precisely because it sits so deep in the obscured band. It is one of the most massive galaxy clusters in the nearby universe, holding the mass of perhaps 1,000 trillion suns. A tremendous swarm of galaxies bound together by their mutual gravity, with hot gas pooled in its centre at temperatures of tens of millions of degrees, glowing in X-rays. And yet, because it lies behind the dust and stars of the Milky Way's plane, it went largely uncatalogued while astronomers were busy mapping far more distant clusters in the clear parts of the sky. One of the most important structures in our cosmic neighbourhood was hiding in plain sight, drowned out by the glow of home. When astronomers finally measured it properly, in the 1990s and after, they realised the Norma Cluster sits very near the centre of the Great Attractor region, very near the bottom of our Great Basin. For a while it seemed the mystery might be solved, that the Norma Cluster simply was the Great Attractor, the great mass doing all the pulling. But the numbers did not quite add up. The Norma Cluster is enormous, but even it is not massive enough by itself to account for all the streaming, all the falling of the entire vast region that pours toward the Great Attractor. It is a major part of the answer. It is not the whole answer. This is part of what makes the Great Attractor such a subtle thing. It is not a single object you can point to and say, there, that is what pulls us. It is a region, a great crowded valley floor, where the Norma Cluster and several other clusters and groups all gather together, their combined gravity summing into the pull we feel. And even all of that, all the visible mass we can now finally see in the once hidden zone, still falls a little short of explaining the full force of our fall, which is exactly why astronomers eventually looked farther out, to Shapley, and to the pushing void behind us, to complete the picture. No one expects one of the largest nearby clusters of galaxies in the entire universe to remain essentially undiscovered into the modern era, but the Norma Cluster did, hidden behind the brightness of our own galactic plane. No one predicts that when you finally found the great mass at the bottom of your basin, it would turn out to be not quite heavy enough, sending you searching even deeper. And absolutely no one anticipates how the universe keeps doing this, answering one question only by opening a larger one behind it, basin behind basin, cluster behind cluster, all the way out. No one expects the most important nearby structure in the universe to spend decades hidden behind a stripe of dust, but that is exactly what happened. No one predicts that a fifth of the whole sky would stay blank on our maps well into the modern age, not because nothing was there, but because too much was here, in the way. And absolutely no one anticipates the strange humility of the lesson, that the hardest thing in the universe to see clearly turned out to be the thing standing closest to home, the thing we are part of, the bright body of our own galaxy. What the new eyes revealed when they finally pierced the veil was not quite what the seven samurai had imagined. The Great Attractor was real. But it was not, it turned out, the whole story. It was more like a way station, a great gathering place along the path of our fall, and beyond it, farther out, something even larger was waiting. To see that, we have to pull back, far back, and look at the entire structure our galaxy belongs to, a structure so vast it was only mapped and named in the last decade. In 2014, a team of astronomers led by R. Brent Tully at the University of Hawaii did something that changed how we picture our place in the cosmos. They took the streaming motions of more than 8,000 galaxies, the very kind of motions the seven samurai had first glimpsed, and they used them to draw a map. Not a map of where the galaxies are, but a map of where they are flowing. And when they drew the lines of flow, a structure appeared that no one had ever seen whole before. Here is the idea, and it is a beautiful one. Imagine you could see every drop of rain falling across an entire continent, and for each drop you could see which way it was running once it hit the ground. You would see the water sorting itself, some draining toward one ocean, some toward another, and between them a dividing line, a ridge, a watershed, where the flows split and went their separate ways. Everything on one side of the ridge belongs to one great basin, everything on the other side belongs to another. The watershed defines the basin, even if you cannot see the basin's edges directly. You define the whole by the way everything inside it flows toward a common low point. Tully and his team did exactly this, but with galaxies instead of raindrops, and with the flow being the streaming of galaxies under gravity instead of water running downhill. They mapped the flows of all the galaxies around us and looked for the watershed, the dividing surface where galaxies on one side stream toward our region and galaxies on the other side stream away toward somewhere else. And they traced out, for the first time, the full basin that we belong to. Every galaxy whose flow drains toward our common gravitational valley is part of one single enormous structure. They named it Laniakea, a Hawaiian word meaning immense heaven or immeasurable heaven. And it is immeasurable very nearly. Laniakea is about 500 million light years across. It contains the mass of about 100,000 trillion suns, something like 100,000 galaxies, all of them flowing very slowly toward a common bottom of the basin. And that bottom, the great gravitational low point toward which all of Laniakea drains, the focus of all that flow, is the Great Attractor. The thing the seven samurai discovered was not a mysterious object sitting alone. It was the bottom of the valley we all live in. It was the drain of our basin, the place toward which our whole immense heaven is slowly falling. Our galaxy, the entire Milky Way, sits far out toward one edge of Laniakea, near its outer rim. We are not at the center of anything. We are a single grain of light out near the boundary of one great basin among many, sliding slowly down its inner slope toward the distant low point in Norma, toward the Great Attractor, along with 100,000 other galaxies all making the same long fall. But here is where the story deepens, because the Great Attractor turned out not to be the final answer to the question of what is pulling us. When astronomers looked more carefully at the flows and measured the motions even more precisely, they found that the Great Attractor itself, the bottom of our basin, is not at rest. It too is moving. It too is being pulled towards something even larger and farther away. Beyond the Great Attractor, about 650 million light-years from us, lies one of the most massive concentrations of galaxies in the entire nearby universe. It is called the Shapley Supercluster, and it contains the mass of more than 10,000 galaxies packed into one tremendous region. The Great Attractor is pulling us, and Shapley, larger still, is pulling the Great Attractor, and us along with it. We are falling toward a low point, and that low point is falling toward a deeper one. Tonight, we're going to spend a little time on Shapley, because it deserves it, and because it is the largest single thing pulling on us that we can actually see clearly. The Shapley Supercluster lies about 650 million light-years away, well beyond the Great Attractor, in the same general direction, the southern constellation of Centaurus. It is named after Harlow Shapley, the astronomer who first noticed an unusual concentration of galaxies in that part of the sky back in the 1930s, though he had no idea at the time what he was looking at. What he had stumbled onto was the most massive concentration of galaxies in the nearby universe, the largest gathering of matter within about 1 billion light-years of us. Shapley contains the mass of something like 10,000 trillion suns, packed into a region a few hundred million light-years across. It is made of more than 20 individual galaxy clusters, each one a great swarm of galaxies in its own right, all bound together into a single colossal structure, the richest, densest gathering of matter in our entire cosmic region. If the Great Attractor is the floor of our local basin, Shapley is something like the deepest point in the whole nearby landscape. A great gravitational pit toward which not only we, but the Great Attractor itself and many other structures besides, are all slowly falling. For years there was a genuine debate about how much of our motion is due to the Great Attractor and how much is due to Shapley behind it. The honest answer, as the measurements improved, is that it is both layered together. A good portion of our fall is the local pull toward the Great Attractor region, the Norma Cluster, and its companions, but a significant share, perhaps almost half, by some estimates, comes from Shapley farther out, reaching across an even greater distance with its even greater mass. We are falling toward the nearer thing and the farther thing at once, and the farther thing is, astonishingly, contributing nearly as much to our motion, despite being more than 4 times as distant, simply because it is so enormously massive. Pattern interrupt. Hold the layered picture in your mind because it is the true shape of our fall. We are drawn toward the Great Attractor, the floor of our own basin. The Great Attractor is drawn toward Shapley, the deeper pit beyond. And it is entirely possible, even likely, that Shapley itself is drifting towards some still larger concentration we have not fully mapped, farther out, deeper in the dark. Each great mass we find pulling on us turns out to be falling toward a greater one. There may be no bottom to the staircase, only landings, each one a vast gathering of galaxies that seemed, for a while, like it might be the final floor. No one expects the chain of pulls to run so deep, attractor behind attractor, supercluster behind supercluster. No one predicts that a structure 4 times more distant than the Great Attractor could pull on us nearly as hard. But Shapley does, by the sheer weight of its 10,000 trillion suns. And absolutely no one anticipates that even Shapley, the great pit of our nearby universe, is itself in motion, falling, like everything else, like us, through the silent dark towards something deeper still. No one expects the thing pulling them to itself be falling towards something bigger, but that is the structure of the universe on these scales. Basins within basins, valleys draining into deeper valleys. No one predicts that the mysterious Great Attractor would turn out to be a way station, a bottom that is also a slope, the focus of our flow, and yet itself in flight toward Shapley. And absolutely no one anticipates the final twist, the one that turned the whole picture inside out, because in 2017 a team of astronomers proposed that we are not only being pulled from in front, we may also be being pushed from behind. Their idea was this: we have spoken all night about being drawn toward great masses, the Great Attractor, Shapley, the crowded clusters of galaxies in the south, but a region with very few galaxies, a great emptiness, a void, has the opposite effect. If you are sitting beside a vast region that is nearly empty, then there is less matter on that side to pull you, and so the pull from the other side wins, and you are effectively pushed away from the emptiness. The astronomers, led by Yehuda Hoffman, found that on the far side of the sky from the Great Attractor, opposite to the direction we are heading, there lies an enormous, underdense region, a great void, and that our motion is partly explained by being pushed away from it. They called it the Dipole Repeller. We are being drawn toward the crowded south and pushed from the empty north at the same time, and the two effects add together to carry us along. The idea that we are being pushed, not only pulled, deserves a closer look, because it is one of the more counterintuitive ideas in cosmology and one of the more recent, and it changes the feel of the whole picture. For decades, the entire conversation about our motion was about attraction. The Great Attractor, Shapley, the crowded clusters of the south. We asked, always, what is pulling us, as though the only way to move a galaxy were to dangle a great mass in front of it. And that instinct is natural. Gravity attracts, mass pulls. So we went looking for masses. But gravity has a subtler side when you think about a whole crowded universe at once. Imagine you are standing in the middle of a large room full of people, and everyone in the room is gently pulling you towards themselves. If the people are spread evenly all around you, all those little pulls cancel out, and you feel nothing. You stay put. But now imagine one whole corner of the room is empty. No people at all, while the opposite corner is packed with a crowd. The crowd pulls you toward it. The empty corner pulls you not at all, and so you drift toward the crowd and away from the emptiness, even though nothing is actively pushing you. The emptiness behaves, in its effect on you, exactly as if it were shoving you away, simply because it fails to pull you the way a crowd would. This is what Yehuda Hoffman and his colleagues proposed in 2017, when they mapped not just the masses around us, but the empty regions too, and traced the full pattern of our motion. They found that opposite the direction of our travel, on the far side of the sky from the Great Attractor, there sits a vast underdense region, a great void, emptier than the average universe. And our motion, they showed, is not only the pull of the crowded south, it is also the effective push of that empty north. They named the void the Dipole Repeller, because it forms, together with the Great Attractor, the two ends of the dipole, the warm spot and the cool spot, our forward and our backward. We are drawn toward the crowd and repelled by the emptiness, and the two effects are roughly comparable in strength, working together to drive our fall. Pattern interrupt. There is something quietly profound in this, and worth holding before sleep. The emptiness shapes us as much as the fullness does. We tend to think only the somethings of the universe matter. The great masses, the bright clusters, the crowded valleys of galaxies. But the nothings matter too. The voids, the vast empty rooms of the cosmos exert their own kind of influence, not by acting, but by failing to act, not by pulling, but by the absence of pull. And that absence pushes us as surely as any mass. Half of what moves us in the end is a great nothing on the far side of the sky. No one expects to be moved by emptiness, by the simple fact that one direction has less in it than another. No one predicts that a void, a region defined entirely by what is missing from it, could shove an entire galaxy across the universe. And absolutely no one anticipates how evenly the books balance the great crowd ahead and the great emptiness behind, contributing almost equally to the silent fall that carries you, tonight, toward the southern sky. Pattern interrupt. Sit with the full shape of it for a moment, because it is one of the most elegant pictures in modern cosmology. You are not simply falling toward one thing. You are caught between a great attraction ahead and a great emptiness behind, pulled and pushed at once, like a leaf carried on a current that is both flowing toward a low place and away from a high one. The crowded clusters reach for you, the empty void releases you, and the sum of all of it, every pull and every push from the entire arrangement of matter around us, is that steady 1.3 million miles an hour toward Norma, toward the Great Attractor, toward immense heaven's distant floor. We have spoken of Laniakea as our home, the great basin we belong to, and so it is. But it is worth knowing that Laniakea is not alone, that it is one basin among many, neighbours upon neighbours stretching across the nearby universe, because it situates us, and the company turns out to be grand. Just as a watershed on Earth has neighbouring watersheds beyond its dividing ridges, each draining toward its own river and sea, Laniakea has neighbouring superclusters beyond its boundaries, each one a great basin of galaxies flowing toward its own attractor. When Tully and his team mapped the flows and drew the watershed line of Laniakea, they also mapped, just past its edges, the borders of the neighbouring basins and gave us, for the first time, a map of our supercluster among its peers. There is the Perseus-Pisces Supercluster, one of the largest and most striking structures in the nearby universe, a great long chain of galaxies, a filament of the cosmic web, so prominent it has been known and admired for a long time, lying off beyond one edge of Laniakea. There is the Coma Supercluster, anchored by the great, rich Coma cluster of galaxies, a dense and famous gathering. There is the Shapley concentration we have already met, so massive it pulls on us across the boundary of our own basin. And there is the Hercules Supercluster, and others besides, each one a vast watershed of galaxies, each one with its own great low point, its own attractor, its own slow inward flow. Our immense heaven is one tile in a great mosaic of immense heavens, each draining its own way, the boundaries between them traced by the delicate dividing lines where the flows reverse. And these superclusters are themselves strung along the filaments of the cosmic web, separated by the great voids, the vast, empty bubbles. The whole nearby universe, when you map it by its flows, becomes a landscape of basins and ridges and hollows, a topography of gravity, with Laniakea our home valley, Perseus Pisces and Coma, and the others the neighbouring valleys, the great voids, the high empty ground between, and the rich Shapley concentration a deep pit, drawing several basins toward it at once. It is a map not of where things are, but of where everything is going, the great slow drainage of the cosmos. Pattern interrupt. Hold the scale of this for a moment because it stacks up so beautifully. You are in a room, in a house, on a continent, on the Earth. The Earth is in the solar system is in the Milky Way is in the local group. The local group is in the Laniakea Supercluster, and Laniakea is one basin in a vast neighbourhood of superclusters woven into the cosmic web, which stretches on, in every direction, for as far as any telescope has ever seen. Every one of those layers is real, nested inside the next, and you are resting right now at the very centre of your own small layer, while all the greater layers carry you gently along. The map runs from the blanket over you to the largest structures in existence, and there is no gap anywhere in the chain. No one expects our great supercluster to be merely one basin among many. Neighbours stretching off, in every direction, each its own immense heaven. No one predicts that the whole nearby universe, mapped by its flows, becomes a quiet landscape of valleys and ridges and empty high ground, a topography you could almost walk. And absolutely no one anticipates how perfectly the scales nest inside one another, room within world within galaxy, within group, within supercluster, within the endless web, every layer carrying you, every layer real, all the way down to the still point where you lie. Before we get started on the settled science, there is a stranger chapter to this story, one that is genuinely unresolved. And because tonight is about honesty as much as wonder, it deserves its place. It is the puzzle that some astronomers have called dark flow, and the careful thing to say about it is that we are not sure it is real. Here is the claim. In the late 2000s, a team of researchers led by Alexander Kashlinsky studied the motions of distant galaxy clusters very far away and reported something they did not expect. Expectation. Distant clusters should drift every which way with no grand coordination. Reality. The clusters, they said, seemed to be streaming together in a single direction, a great coherent flow across a region so enormous that the ordinary pulls of the cosmic web should not be able to coordinate it. And the direction of this supposed flow pointed out beyond everything we can see, towards something past the edge of the observable universe, some great influence from a region we can never directly observe. They called it dark flow, a great mysterious current with no visible cause within our horizon. If it were real, it would be staggering. It would suggest that the arrangement of matter we can see, the Great Attractor Shapley, the whole cosmic web within our view, is not the full story, that there is some vast tilt to the universe beyond the edge of what we can ever observe, pulling everything we know gently to one side. It would be a hint of something outside the visible cosmos, felt only through its faint, coherent tug on the most distant clusters. It is the kind of idea that, if confirmed, would reshape our understanding of the universe on the largest scales. But here is the honest part, and it matters. Dark flow is contested, and most cosmologists today are skeptical of it. The measurement is extraordinarily difficult, working at the very limit of what the instruments can detect, and other teams analyzing similar data have not consistently confirmed it. Later measurements, including from the very precise Planck satellite, found little or no evidence for such a flow, and many researchers now believe the original signal was likely an artifact, a subtle error rather than a real current. The matter is not entirely closed, and a few researchers still pursue it, but the weight of evidence has moved against it. The careful, truthful statement is that dark flow was a fascinating claim that, so far, has not held up and probably is not real. I tell you about it anyway on a night meant for rest, because it captures something true about how this science actually works. Not every intriguing signal turns out to be a discovery. Some are real, like the Great Attractor, confirmed and refined over decades. Others, like dark flow, shimmer for a while at the edge of the data and then fade as better measurements come in. Both are part of the honest map. And there is something quietly reassuring in that. In a science willing to say, we thought we saw something vast beyond the horizon, and we looked harder, and we are no longer sure, and that is all right. No one expects every great claim to survive, and dark flow may not, dissolving back into the noise from which it briefly seemed to rise. No one predicts which faint signals at the edge of the possible will firm into discoveries and which will gently fade. And the only way to find out is to keep measuring. And absolutely no one anticipates how much trust a science earns precisely by being willing to let go of its most dramatic ideas when the evidence will not hold them, keeping only what survives the hardest looking. Now, let's begin by turning the other way for a moment. Before we follow the great fall outward to its end, it is worth turning the other way for a moment inward to look at our own immediate neighborhood and how it fits into all this motion, because we are not falling toward the Great Attractor alone. We are falling as a family. The Milky Way is not a solitary galaxy adrift. It belongs to a small, tight-knit cluster of galaxies called the Local Group, a gathering of some dozens of galaxies bound together by their mutual gravity, spread across a region a few million light-years wide. Two great spiral galaxies dominated our own Milky Way and the Andromeda Galaxy, with a third smaller spiral, the Triangulum Galaxy, and then a scattering of several dozen smaller dwarf galaxies orbiting the two giants like moths around two lanterns. This is our home group, our immediate family. The galaxy's gravity has permanently bound to us, and the local group moves as a unit. When we speak of the Milky Way falling toward the Great Attractor at over 1,000,000 miles an hour, we are really speaking of the whole local group falling together, the Milky Way and Andromeda and all their companions carried as one body on the great current. Within the group, There are smaller motions, the Milky Way and Andromeda are actually drifting toward each other, and will eventually meet and merge billions of years from now. But all of those internal motions ride on top of the group's shared Great Fall toward the south. We move within our family, and our family moves within Laniakea, and Laniakea drains toward the Great Attractor. Motion within motion within motion, each nested inside the next. This nesting is the true structure of everything tonight. You orbit the Earth's center as it spins. The Earth orbits the Sun orbits the galaxy. The galaxy moves within the local group. The local group falls through Laniakea toward the Great Attractor, and Laniakea, with the Great Attractor at its floor, drifts toward Shapley beyond. 6 layers of motion, each one real, each one carrying the one inside it. From the spin beneath your feet to the great supercluster currents at the top. You are riding all 6 at once this very moment in perfect silence, and you feel not a single one of them. Pattern interrupt. There is a particular comfort in the local group, and I want to name it because it returns at the very end of our story. Everything else we have spoken of tonight, the Great Attractor, Shapley, all the distant crowded valleys, the expanding universe will eventually carry beyond our reach. But not the local group. Our own family is bound tightly enough that gravity holds it together against the expansion, permanently. The galaxies we are falling toward we will lose. The galaxies we are falling with we will keep. In the deep future, when all the distant structures have receded over the horizon and vanished, the local group will remain, drawn together into a single great island of stars. The great fall toward the Great Attractor is a reaching toward what we cannot keep. The local group is what we hold on to while we reach. No one expects to discover that they fall not alone, but as part of a family, the whole local group carried together on the same great current. No one predicts that of all the structures pulling on us and pulled toward, only the nearest, our own little group, is truly ours to keep. And absolutely no one anticipates how the two facts sit together so gently, that we are bound forever to our nearest companions and forever falling toward distant things we will never reach, and that both, somehow, are reasons for peace. Before we get started on the larger picture, to truly understand where the Great Attractor sits, we need to pull back even further than Laniakea and look at the largest pattern in all of nature, the great architecture into which every galaxy, every cluster, every supercluster is woven. Astronomers call it the cosmic web, and once you have seen it, you can never again picture the universe as galaxies simply scattered through empty space. When astronomers map the positions of millions of galaxies in 3 dimensions, a structure emerges that looks startlingly organic. The galaxies are not spread evenly. They are strung along immense threads called filaments, like beads of dew along the strands of a spider's web. Where the filaments cross and tangle, the galaxies pile up into dense knots. The great clusters and superclusters, the crowded valleys like the Great Attractor and Shapley. And between the filaments lie the voids, enormous, rounded emptinesses, vast bubbles of nearly perfect nothing that make up most of the volume of the universe. Threads of galaxies wrapped around great hollow voids, knots where the threads meet, all of it stretching on in every direction for billions of light years. That is the true large-scale shape of the cosmos, a web, a foam, a great cosmic sponge. And this web is not random. It grew over billions of years from the faintest ripples in the early universe, tiny regions that started out very slightly denser than average. Gravity, given enough time, is a patient sculptor. The slightly denser regions pulled in a little more matter, which made them denser still, which let them pull in more, and over the long ages the matter drained out of the emptier regions and gathered along the threads and into the knots, carving the voids ever emptier and the filaments ever sharper. The cosmic web is the frozen record of that great, slow gathering, gravity's signature written across the whole universe. Now place our story inside that web. The Great Attractor is a knot, a place where several filaments of the cosmic web converge and the galaxies pile up. Laniakea is the great basin draining toward that knot. Shapley is a larger, denser knot farther along the web, and the Dipole Repeller, the great emptiness pushing at our backs, is a void, one of the web's vast, hollow bubbles. We are not falling through featureless space toward a lonely mass. We are sliding along a strand of the cosmic web, drawn toward the knot where our strand meets others, pushed from the void our strand borders. Our great fall is simply the motion of one galaxy following the threads of the largest structure there is toward the place those threads gather. Pattern interrupt. Hold the whole picture for a moment because it is one of the most beautiful in all of science. Every galaxy you have ever seen in a photograph, every smudge of distant light, sits somewhere on this vast web, on a thread, in a knot, at the edge of a void. And every one of them is doing exactly what we are doing, sliding slowly along its strand toward its nearest knot, drawn by the gathered mass, the whole universe very gradually flowing along the filaments, draining toward the great crossing points, growing slowly clumpier and emptier as the ages pass. We are one bead of dew on one strand of one small corner of an endless web, following the thread home. No one expects the universe to have a shape, a structure, an architecture you could almost run your hand along, but it does, and it is the cosmic web. No one predicts that the mysterious Great Attractor would turn out to be simply a knot where the threads of that web converge, an ordinary feature of an extraordinary pattern, and absolutely no one anticipates how the largest structure in existence grew from the smallest of beginnings, faint ripples in the newborn cosmos combed by gravity over billions of years, into the great glowing web we are woven into tonight. Tonight, we're going to pause in the middle of all these vast numbers and bring the scale of this back to something the body can almost hold, because the distances we have been throwing around are so large that they stop meaning anything, and that is a kind of loss. Try this. Shrink the entire Milky Way galaxy, all 100,000 light years of it, all 400 billion stars, down to the size of a single dinner plate. At that scale, our nearest large neighbour, the Andromeda Galaxy, is another dinner plate about 15 feet away. The whole local group, our little family of galaxies, fits in a large room. And on that same scale, where our entire galaxy is a dinner plate, how far away is the Great Attractor? It is about 1/4 of a mile away. Our galaxy, a dinner plate, falling slowly across 1/4 mile of empty space toward a great crowded region we cannot quite see. And Shapley, the deeper pit beyond, is more than a mile off on this scale. The distances are so enormous that even when you shrink our entire galaxy to something you could hold in 2 hands, the thing pulling us is still blocks and blocks away through the dark. Now hold the time. We are crossing that space at over 1,000,000 miles an hour, which sounds tremendous, and is. But the distances are so vast that even at that speed the fall is almost imperceptibly slow against the great clock of the cosmos. In the entire history of the Earth, 4.5 billion years, our galaxy has fallen toward the Great Attractor by only a small fraction of the way. The dinosaurs lived and died while we crept a little nearer. All of human history, every empire, every life, every night anyone has ever slept, has passed in a span during which our galaxy's great fall has moved us a distance that, on the dinner plate scale, you could not measure with any ordinary ruler. The motion is enormous, and the distances are more enormous still. And so the fall, for all its speed, is gentle beyond imagining, a lean so slow that 100,000 human lifetimes would not let you see it move. Pattern interrupt. This is the thing I most want you to carry into sleep, the reconciliation of the two feelings this subject stirs. On one hand, there is the vertigo, the strangeness of learning you are hurtling through space at over 1,000,000 miles an hour toward an unseen mass. On the other hand, there is this, the realization that the distances are so vast and the timescales so deep that the whole tremendous motion is, from where you lie, utterly serene. Both are true. You are moving faster than any human machine has ever traveled, and you are also, for all practical purposes, perfectly still, because the place you are falling toward is so unfathomably far that your entire life and the lives of everyone you will ever know will not bring it appreciably closer. No one expects speed and stillness to be the same thing, but at the scale of galaxies, they very nearly are. No one predicts that a motion of over 1,000,000 miles an hour could be so gentle that the rise and fall of whole species passes before it shifts you any meaningful distance, and absolutely no one anticipates how comforting that is in the end, that the great fall is real and you are truly in it, and that it will cradle you through this night and every night exactly as it has cradled every sleeping creature that ever lived, without haste, without sound, without ever once arriving. So we come at last to the question that has been waiting underneath this whole journey. We are falling toward the Great Attractor at over 1,000,000 miles an hour. We have been falling toward it since before the Earth had oceans. Where does the fall end? Will we ever arrive? The answer is no. And the reason is the strangest and most important fact in all of modern cosmology. We will never reach the Great Attractor. We will never arrive at Shapley. Because while everything we have described tonight is real, the gravity, the streaming, the great basins and the pull toward their floors, all of it is happening against a background that is winning. The universe is expanding and the expansion is accelerating. Space itself is stretching faster and faster, carrying the distant structures away from us more quickly with every passing age. The Great Attractor is pulling us toward it, but the space between us and the Great Attractor is growing faster than our fall can close it. We are running toward a destination that is receding from us more quickly than we approach. We will never get there. We have said, more than once, that we will never reach the Great Attractor because the expansion of the universe is carrying it away faster than we can fall toward it. That is such a strange and important claim that it deserves its own unhurried explanation, because it rests on one of the most startling discoveries in the history of science. For most of the 20th century, astronomers knew the universe was expanding, but they assumed the expansion must be slowing down. It seemed obvious. All the matter in the universe pulls on all the other matter by gravity, and gravity is attractive. So the mutual pull of everything should be gently braking the expansion, slowing the galaxy's retreat over time. The way a ball thrown upward is slowed by the Earth's pull. The only real question, astronomers thought, was whether the universe had enough matter to eventually halt the expansion and reverse it, or whether it would coast outward forever, slowing but never quite stopping. Either way, the expansion should be decelerating. Then, in 1998, two competing teams of astronomers measured it directly by observing a particular kind of exploding star in very distant galaxies, stars that detonate with nearly the same true brightness and so serve as reliable distance markers across billions of light years. They expected to measure the expansion slowing down. Instead, they found the opposite. The expansion is speeding up. Over the last several billion years, the stretching of space has been accelerating, the distant galaxies flying apart faster and faster, not slower. Something is pushing the universe open, overpowering the collective gravity of all its matter, driving everything apart at an ever-increasing rate. Astronomers gave this something a name that frankly admits how little we understand it. They call it dark energy. We do not know what dark energy is, we know only its effect, that it pervades all of empty space and that it pushes, driving the accelerating expansion. It is, by the measurements, the dominant ingredient of the universe. More than 2/3 of all the energy there is, a vast unseen pressure woven into the vacuum itself. And it is dark energy that seals the fate of our great fall. Because as space expands faster and faster, the distance between us and the Great Attractor grows faster and faster too. Our fall continues, our speed real, our direction fixed, but the finish line recedes more quickly than we close on it. We are running toward a destination on a track that is stretching beneath our feet, and the stretching is winning and will only win more decisively as the ages pass. Pattern interrupt. Here is the full and final shape of our fall then, and it is worth holding clearly before we speak of the deep future. Gravity reaches for us the Great Attractor and Shapley and all the crowded valleys of the south, drawing us on at over 1,000,000 miles an hour. And dark energy pushes everything apart, stretching the space we are falling through, carrying our destination away. The fall is real, and the fall is endless. And the fall never arrives, not because we slow down, but because the road itself keeps growing longer, faster than we travel it, forever. No one expects the universe to be flying apart faster and faster against all the pull of its own gravity, but it is, and we have measured it. No one predicts that the dominant ingredient of all reality would be a thing we cannot see and do not understand, a pressure in the vacuum that drives the cosmos open. And absolutely no one anticipates that this strange dark energy is the very thing that decides the end of our story, the reason the Great Attractor's long pull will never deliver us, the reason our great fall is, and always will be, a reaching that never closes. Over the coming billions of years, this only grows more true. The acceleration strengthens its grip. The distant galaxies, the far clusters, the Great Attractor itself, all of it will slowly recede beyond our reach, carried away on the swelling of space until one day, in the deep future, they will slip past the horizon of what we can ever see or touch and be gone. Our long fall toward immense heaven's floor will quietly become a fall toward a place that no longer exists for us, a destination carried over the edge of the visible world. And yet, here is what the fall does keep. It cannot deliver us to the Great Attractor, but it has already bound us permanently to the things closest to us. The Milky Way and Andromeda and the small galaxies around them, our own local group, are held together by a gravity strong enough to defeat the expansion on that small scale. We will not reach Shapley, but we will keep our nearest companions. In the deep future, as everything else recedes and vanishes, Our own little family of galaxies will draw together, merge, and form a single great island of stars, alone in an emptying sky, while the rest of the universe slips away. The fall toward the Great Attractor was never going to arrive, but the fall taught us who we will keep and who we will lose, and how the whole vast arrangement is quietly coming apart, even as the nearest pieces of it draw close. Tonight, we're going to go all the way to the end now, to the deep future, and follow our great fall to its true conclusion, because the story of where we are going is, in the end, also the story of how the universe grows lonely. Begin close to home. In about 4 billion years, long before our fall toward the Great Attractor has carried us any meaningful distance, our own local group will rearrange itself. The Milky Way and the Andromeda Galaxy, the two great spirals drifting toward each other, will meet. It will not be a collision of crashing stars, because the stars within galaxies are so far apart that almost none of them will ever strike one another. It will be a slow gravitational merger, the two great wheels of light passing through and around each other over hundreds of millions of years, flinging out long streamers of stars, settling at last into a single vast elliptical galaxy. Astronomers have already given the future galaxy a name, half in jest, Milkdromeda. Our descendants, if any exist, will live not in a spiral, but in that great merged island of stars. Now pull the timeline forward, far forward, billions upon billions of years. All the while the accelerating expansion is at work, carrying the distant galaxies away from us faster and faster, and carrying the Great Attractor and Shapley and every far structure steadily out of reach. One by one, over the deep ages, the distant galaxies will redden and dim and slip beyond the horizon of what we can see until eventually they are gone, their light no longer able to cross the ever-widening gulf to reach us. The sky will slowly empty. The great cosmic web, all its threads and knots and the crowded valleys we are falling toward, will recede into invisibility, swept away on the swelling of space. And here is the lonely heart of it. In that far future, a watcher in our merged Milkdromeda galaxy will look out at the sky and see only their own galaxy of stars, surrounded by darkness. The other galaxies will be gone, carried beyond reach and beyond sight. The Great Attractor, our great destination, will long since have vanished over the horizon. Such watchers, if they have no record of what came before, might reasonably conclude that their single galaxy is the entire universe, alone in an empty void, with no sign that there was ever anything else. The very knowledge we hold tonight, the knowledge of our fall, of Laniakea, of the Great Attractor, will have become unrecoverable, erased by the expansion, a truth that could only be known by creatures who happened to live early, while the light still reached across the dark. Pattern interrupt. There is a strange tenderness in this, and it is the thought I most want to leave with you. We are falling toward the Great Attractor, and we will never reach it, and in the deepest future it will not even be visible to our descendants. And yet we, here, tonight, can see it. We live in the brief, bright era of the universe when the great structures are still in view, when the fall can still be traced, when the immense heaven of Laniakea still glows on our maps. We are not too late. We are, if anything, blessed by being early, alive in the one age when the truth of our motion is still written legibly across the sky. The future will lose this knowledge. We have it now. No one expects the universe to grow lonely, the galaxies vanishing one by one over the horizon until only our own remains. But that is the future the expansion is writing. No one predicts that the very thing we are falling toward will one day become invisible to those who come after us, our great destination erased from their sky, and absolutely no one anticipates how that turns the present into a kind of gift, that we are alive in the rare window when the great fall can still be seen and known and traced before the long expansion draws the curtain and the universe forgets the shape of itself. Tonight, we're going to look at why this story is not finished, that the map of our great fall is still being drawn, and that the next 10 years will sharpen it more than the last 40 did. The reason is a new generation of instruments and surveys, machines designed precisely to map the positions and motions of galaxies across enormous volumes of space. There is a long-running program called Cosmic Flows, led by the same Brent Tully who named Laniakea, which has been steadily measuring the true distances and motions of more and more galaxies, edition after edition, each one filling in the great flow map with finer detail. With every new release, the basins grow clearer, the watersheds firmer, the streaming better understood. The picture of Laniakea and of the Great Attractor at its floor and of Shapley beyond grows more precise each year, and there are great new eyes opening. The Vera Rubin Observatory in Chile, which began full operations recently, will photograph the entire southern sky over and over for 10 years, cataloguing billions of galaxies and measuring their positions with unprecedented reach. Survey telescopes are pushing deeper into the zone of avoidance than ever before, chasing down the last hidden structures along the galactic plane. Radio arrays of extraordinary sensitivity are mapping the hydrogen gas of galaxies across vast volumes. Each of these will add to our understanding of the great currents, refining the speed and direction of our fall, testing whether the Dipole Repeller is exactly as proposed, searching for whatever may lie deeper still beyond Shapley. There are real open questions waiting for these instruments. We still do not fully agree on how much of our motion comes from the nearby Great Attractor and how much from distant Shapley, and better data will settle it. We still suspect that more mass may hide in the narrowest, dustiest part of the Zone of Avoidance, and deeper surveys may yet reveal it. And there are deeper puzzles too, hints in some measurements of streaming motions on scales so large they are difficult to explain. Motions that, if confirmed, would test our very understanding of how the universe grew its structure. Most of these hints are contested, and the careful answer to many of them is that we do not yet know. But that uncertainty is not a weakness. It is the live edge of a science still in motion, still mapping the great fall we are all part of. No one expects a story this old, the discovery of our motion now, decades behind us, to still be opening new chapters, but it is. No one predicts how much the map will sharpen as the new surveys pour in, how the basins and flows we have sketched tonight will firm into precise cartography within the coming years. And absolutely no one anticipates what may yet be found in the last unmapped strip behind our galaxy's heart, or in the deep distance beyond Shapley, where the staircase of attractors may descend to landings we have not yet seen. The fall is ancient. The mapping of it has only just begun. Let us gather the whole journey now gently, the way you would gather the threads of a long day before sleep. We are moving. The entire Milky Way, every star in it is falling through the universe at about 1.3 million miles an hour. And we measured that speed against the oldest light there is, the warm spot and cool spot in the afterglow of the Big Bang. We are falling toward a great unseen mass in the southern sky, in the direction of Centaurus and Norma, a mass so large the astronomers who found it could only call it the Great Attractor. It hid from us for decades behind the dust and glow of our own galaxy, in the blind stripe we call the Zone of Avoidance, until new eyes, infrared and radio and X-ray, finally pierced the veil. And when we pulled back far enough to see the whole shape of it, we found that the Great Attractor is the floor of the great basin we belong to, an immense heaven called Laniakea, 100,000 galaxies all draining toward the same low point, while that low point itself slides toward the deeper mass of Shapley beyond, and a great emptiness pushes gently at our backs. No one expects to learn that the ground they stand on is falling. No one predicts that the fall has no destination, that it is a reaching towards something the expanding universe will never let us hold. And absolutely no one anticipates how peaceful that turns out to be once you let it settle. Because the lesson of the Great Attractor is not that we are doomed to a journey without arrival. The lesson is that we have always been moving gently, silently, carried on the great slow currents of gravity and emptiness, and it has never once disturbed a single quiet night on Earth. The most enormous motion you are part of asks nothing of you. It did not wake you. It will not wake you tonight. So let the fall carry you the way it always has, without effort, without sound. You are moving at over 1,000,000 miles an hour toward a vast unseen thing across an immense heaven, and you are also lying perfectly still, warm and safe in a quiet room at the end of a day. Both of those are true. They have always been true, and the falling, the endless, gentle falling of the whole galaxy through the dark turns out to feel exactly like rest. The Milky Way is falling. Laniakea is flowing. The Great Attractor is reaching for us across a gulf we will never cross, and the empty places are pushing softly at our backs, and the whole immense heaven is sliding through the night toward a floor it will never reach, and you are here, inside all of it, held and carried and perfectly still. Sleep well tonight. Good night.